In this video, I will show you how machine learning is used to find exoplanets. So, exoplanets are those planets which are not from our solar system. There are five ways to find an exoplanet, namely radial velocity, transit method, direct imaging, gravitational microlensing, and astrometry. Out of these methods, these two are the most commonly used. Let me show you a video. So this is the working of transit method. In this method, when an exoplanet passes through its sun, then we observe a dropping in the light coming from that sun over a period of time. And this effect can be measured periodically, like in every 2 days, 2 months, or any time. So this gives us an idea that there is a probability of having an exoplanet around that sun. So this presentation is for one planet, and sun can have multiple planets like in our solar system. So this is how light dropped every time when an exoplanet passes through the sun. But this method has a major drawback that we can only detect the exoplanets whose axis of revolution is horizontally parallel to ours. Otherwise, we won't be able to detect them. There are other methods also. You can watch this video on how exoplanets are found. I'll put a link to this video in the description. We are going to learn how machine learning is used to detect these exoplanets. So, what is machine learning? Machine learning is the result of general AI that involves developing machines that can deliver results better than humans. In machine learning, we give some data and we also give its output in supervised learning. And a machine learning model is trained over that data input and output. And this program will then learn to give us answers or output for unseen data or some other data that is not present, that will be generated in the future. So the basic approach of machine learning is that we are going to build some model. We have to train our model, and then our model will be able to predict some outcomes on test data or new data that is unseen by it. Now let's explore how scientists use this machine learning to find exoplanets. I am referencing this article for building our model to find exoplanets. So here the basic concept is that we have some exoplanets data available on Caltech University website, and you can easily download it from link in description also. So we have our data. This data is from Kepler telescope. It has some parameters or features like name, disposition, score, orbital period, and so there are so many features, and it contains the information regarding whether these are the libraries required for our program. Pandas is used for doing operations on data frame, NumPy on arrays, and matplotlib for plotting the graphs, etc. And there is a famous library used in machine learning known as sklearn. It has some inbuilt functions and classes which we can use. Like here, we are using these many algorithms of machine learning to build our model. Then we have evaluation matrix. These will be used to check the accuracy of our model, errors, etc. and these are just to handle warnings. So let's start. What this line will do is it will store the it will read this CSV file, exoplanets file, and store the values in this data. So data is a data frame. After that, we are renaming the column names, like here cap ID to this capital ID, this one to exoplanet archive disposition, etc. So it's a choice. After that, this data dot head is used to show how our data looks. So you can check the first 5 columns of data. It looks like this. Here you can see the data values are written in form of string. Like string is just some text form. This confirmed candidate, false positive. These are some alphabets or text, or you can say string. So we are going to replace them with numbers. As our machine learning models work on number, so we have to convert them into numbers respectively. We are creating a column name exoplanet candidate in our data, and whose values are going to be according to this statement. So here we are applying a function on this disposition using Kepler data, and we are setting the value equal to 1 when this column value is candidate. Otherwise, we are setting it to 0. Means for candidate, we are setting the value 1, and for false positive, we are setting the value equal to 0. And similarly, we are creating an exoplanet confirmed column in our data, and this will contain the values by applying a function on this column, where the value of the column will be 2 if the column value is confirmed, and it will be set to 1 if its value is candidate, and otherwise it will be set to 0 when the column value is false positive. So after running these two, when I check our data, this data dot head function just show the first 5 values of the data. So when we go and check here, you can see two new columns are created: exoplanet candidate and exoplanet confirmed. And you can match the values here. Like for exoplanet candidate, when the value is candidate, it should be equal to 1. So here you can see 1, 1, 1, and 0 for false positive. Similarly, in exoplanet confirmed, 2 for confirmed, and then 1 for candidate, and false positive is set to 0. So it's perfectly fine till now. After that, we can use these line of codes to check the correlation between these columns. Here we can see the more the color of this column tends toward the white or lighter color, it means they are more correlated. And as the color of the column goes darker, this means these column are not that much interrelated. Like you'll see that diagonal will be always equal to 1, because this cap ID column is same, so they are cap ID, so they are, as they are same, so they have high correlation. And as you can see spot some dark color column, this means that these features are not that much correlated to each other. Like this transit depth upper column is not that much related to this transit depth lower feature. You can just explore these things if you want. After that, we are going to do some columns from our data which we don't require or doesn't create an impact on our model. So these mod these feature columns will be dropped from our data. As you can see initially, we have these cap ID, name, etc. columns, but right now after copying it, when we check data dot head, you can see these columns are no more into our data. Only the columns with numerical value are remain. After that, we are using this line to drop NA. NA means a null value or an empty value. So we are dropping the rows which have some null value. Like for example, if there was nothing or there was null in at this place, then this row will be dropped out of our data. After that, we are using the train test split method of sklearn. To run it. What this method do is it will split the data into train and test, and our test size is 40%. So the 40% of data will be stored to the test, and the 60% data will be stored for training purpose. You can see their shapes, like here we have 4,681 rows, and for test we have 3,122 rows, and the column are these features which are going to be same for both 39 39, and our original data shape was this with 39 columns. So if you add these two rows, then you will get the sum equal to this. Now we are converting our train data into a CSV file. So we can use this file whenever we have to train our model. And after that, let's see our test data. So in our test data, we have an exoplanet candidate and exoplanet confirmed and all other features. So our goal is to find the value for the column exoplanet candidate, whether the object is an exoplanet or not. So it will predict it. So I'm copying this exoplanet candidate value of this test data into some another data frame named as test solution. So now test solution contains the all the values of this column exoplanet candidate, and you can also see them. These are same 11010, etc. After that, I am dropping the exoplanet candidate column from the test dataset, and I'm doing this because we have to predict this column. We are not going to tell our model the value for this column. Our model will be predicting that column, and we are storing it here so that we can match how well our model performed. Is it predicting the correct values or not? So when after dropping the exoplanet candidate value, just look at the test data frame. You can see the exoplanet candidate column is dropped from here. And I'm also going to convert this data frame into CSV files. You can see these files are created here. Now comes the coding part to build our models. So first of all, I had created two functions named evaluation and print results. I'll be using them to check the accuracy and scores, etc. for our models, and also this one for checking the best parameters used. We are creating a data frame named X, which contains the trained data set, but I had dropped the exoplanet candidate from that data. Let's just see once what train.head gives us. So in train.head, as you can see, we have exoplanet candidate here. So right now we are training our model, and in the training part, we have to make tell our model what are the features and what are the label or outcome or target for which our model has to predict. So we have to divide our data set into features and the target column. So the features will contain all the columns except the target one. So exoplanet candidate is our target. So I am taking all other columns of trained dataset in this X except this exoplanet candidate. And you can see the X, it doesn't contain exoplanet candidate. After that, we have to take note of the target or output column. So I am copying this exoplanet candidate column of train data in this Y. After that, we have to create xtrain, xtest, ytrain, ytest data from using this train test split method and pass the value here and the target values here. So our feature are stored in this X and target value is stored in this Y. So I'm using X and Y here. Let's run it. Now we have these four data sets containing xtrain, xtest, ytrain, ytest. You can see the xtrain values. They don't have exoplanet candidate column. And similarly, we have xtest value, which we will be using to predict. And xtrain, we are using this value to train our model. So xtrain and ytrain will be used to train the model. Ytrain contains the solutions or the results for xtrain. Let me show you. If I write ytrain dot head, then this will print the results for exoplanet candidate column, like here 1000. So our model is going to learn these xtrain values, or you can say features, and their respective outcomes or these ytrain values. Whenever I pass some other test dataset containing the same features as this xtrain, then it will be able to give some predictions regarding the target of that test dataset which we passed. So let's see it here. First machine learning model that we are going to use is logistic regression model. So this model will be basically used to classify whether the object is exoplanet or not. I'm creating an instance of this logistic regression model as LR, and this logistic regression model has some parameters which I passed here. You can change them or just use the model without passing them. So I am passing them because it might improve our model. And after that, we have to fit the model to train set. So have to use this command for fitting the model. Here, xtrain and ytrain data, as I told, will be fitted or trained to the model. After that, we are predicting on the test set. So here, as you can see, we created four data sets: xtrain, xtest, ytrain, ytest. So our model is going to train on the xtrain and its respective outcome means ytrain. And now we have to predict or test our model by passing the X test. And whatever outcomes our model gives, we have to match them against this Y test. So if the outcomes provided by our model matches these already known Y test data set, then we can say that it's a good model, and we can think that it will perform good when some other machine data is passed to the model. So here for prediction, we are storing the outcome values or the prediction values by our model in this ypred function, and this command is used to predict X test, we are predicting on the for the X test values. After the prediction is done, we are evaluating our model. So we already know the answer for X test target. Outcome of this X test is already stored in this Y test, and this is the Y pred contain the outcomes that our model predict. So our this function which we created over here will print this matrix for the model. Let me try running it. So here it shows that accuracy of our model is 82% something. It means our model predicted the correct value for 82% test cases, and it predicted wrong for the remaining ones. And these are some other matrices which are used to tell whether a model is good or bad. So one of our aim is to get the as high accuracy as possible. Means we aim to design a model that predicts the correct output most of the times. After that, this confusion matrix contains these four values: true, negative, false negative, and true positive. This true positive means that our model is predicting that the given object is exoplanet, and and we know that the object is actually an exoplanet, so it's a case of true positive. And for false negative, it means that our model says that the object is not an exoplanet, but in actual it is an exoplanet. So we aim to reduce this as much as possible, because we don't want to miss an exoplanet due to our model's inaccuracy. And this is true negative. We can have it comparatively high to this false negative. And here true negative means that our model is saying that the given object is an exoplanet, but it is actually not. So if this is the case, then we don't have any loss. Like our model is saying yes, but it is actually a no. So if we check and found it's a no, then still we don't lose anything. We don't lose the exoplanet. But in false negative, if it's an exoplanet and our model is saying no, then it's a loss case. We might never be able to find that exoplanet again. So these are the values which you might want to consider. After that, uh, we have another model, KNN model, K neighbors classifier, which works on the basis of checking the outcomes of its neighbors. Like if uh, two or three neighboring data sets have similar value to the one we are going to predict, then our model will give outputs based on its surrounding data cases that are similar to that data case. Similarly, here we have some parameters. You can change them accordingly. They might impact the accuracy of our model. So here I am instantiating the model in this KNN, and here fitting of the model is done on X train, Y train. After that, prediction is done over the X test dataset, and evaluation is done similarly. When I run it, you can see its accuracy is showing 78% approximately. So it's a bit less compared to this model. Similarly, we have another classifying machine learning model known as the decision tree classifier. Here, similarly, we are instantiating, fitting, and then predicting over X test. And on the evaluation matrix, you can see it gives a pretty high accuracy. Like it's 99.7. It's around 100% accurate. Means approximately for all the data, all the test data cases, it is giving the correct output almost every time. So as this one gives some high accuracy, I am I want to predict the outcomes for our test data. So I'm storing the results of predictions from our model named tree in this read data frame. So whenever I run it over this test data set, then our model is predicting the outcomes, storing it into this grid. So it's an array. Let's just see the first 20 outcomes of this array. So these are the first 20 outcomes, and you can also match these values with this test solution data frame values. So let's check the first 20 values of this test solution data. So as you can see that our model is predicting 1 and the actual value is also 1, so it's predicting accurately. Let's match for all the let's match for all the values. So 1 1, then 0 1, and again 0 1, and after that we have two zeros and then one two zeros, then 0 1 1 1, and after that all zeros. So as you can see, for the first 20 values we are checking, our model is 100% accurate. And as you can see, I had not trained the model on test dataset values. These are just x and x test. These are from the training data itself. So the test data is new for our model, and this model is predicting the values approximately 100% correct for some new data which it hasn't seen yet. So it's a pretty good thing for our model. Means when we collect some new data from when our telescope collects some new data, we can pass that data to this model and it will help us in predicting the exoplanets. So the one advantage of this thing of predicting using machine learning will be that it saves our time. So generally scientists might took even years for predicting the exoplanet, but our models can predict them into minutes or seconds. And other advantage is that it's very hard for for scientists or human to to compare these values one by one for this huge this much huge data and then telling that it might be an exoplanet or not. But our machine learning models can do them in seconds or minutes. So that's the other advantage. And as you might be seeing the news that AI have been predicting the exoplanet. So these are the basic approach scientists are using to find those exoplanets using AI. They could have models similar to these ones for predicting and then confirming the exoplanet. So it's a lot easier for them to find. And with the increase in uses of finding exoplanets using machine learning, the numbers of exoplanet new findings yearly has increased exponentially. So it's a good thing. And one more model you can try is this one. This one is also giving 99.89%, even greater accuracy than this one. So it's our choice to check which one to use, or we can also use multiple models and then compare the outcomes for higher accuracy. Like we have some ensembling techniques in machine learning. So this was a brief intro kind of video for giving you an idea that how these exoplanets are found using machine learning. And I hope you got the basic idea that first of all we train our models the already known data exoplanet, and after that the model will predict the exoplanet based on the new or test data. So that's all for this video. I hope you liked it. Thanks.